Morning, students. Today, we shall try to analyze the what happens when more than one stage of amplifier is connected in cascade on the lower cutoff frequency. Because we are not talking about higher cutoff frequency because we know higher cutoff frequency, we have just studied in our last lesson that higher cutoff frequency is decided by the transistor's intrinsic properties. But lower cutoff frequency is governed by the various external components that we have chosen. In front of you, there is a two-stage amplifier. There is a one-stage audio amplifier, first stage. There is a second stage, and they are coupled by a coupling capacitor. In fact, this experiment I have done earlier also for you. We repeat once again today for one particular purpose. See, this board plotter, its output is now connected here to the output of the first stage, right? This is a board plotter. We run the board plotter. We stop it. I'll reverse the diagram so that you can see it properly. Here we see the mid-band gain is 37.9 dB. I hope you can see this. Let's say 38 dB. So lower cutoff frequency is 3 dB less frequency, that is 38 minus the 35. So let's try to take this cursor to something like 35, 35.073 dB. And lower cutoff frequency is 172.641 hertz, let's say 172 hertz. So this is the lower cutoff frequency of one single stage. Now let us see what is the lower cutoff frequency when both stages are connected. So this is 172. Remember this figure, 172. I shall connect this output to now the of the second stage and run once again. See, the board plotter has changed. What we can see that gain has increased. Now the mid-frequency gain is 78.629 dB, let's say 78.6 dB. And 3 dB less is 75.6. So 3 dB less is 75.6. Yeah, 75.68 dB. It is 232 hertz. So in one stage, it was 172. In two stage, it is 232. If we can make more accurate measurement, it should be actually double, right? So what do we find? As we cascade more and more stages in an amplifier, the lower cutoff frequency goes higher. That means low frequency performance of the amplifier deteriorates. Why this happens? That is what we are going to discuss today. Now I shall change from this multi-sim window to another window. For that, your screen may interrupt for a second. Yes, we come here. I think now you are with me. Frequency domain analysis of BJT amplifier. In this, we are going to see what is the effect of cascading. This, multi-staging is also now called cascading on lower cutoff frequency. So this is a hypothetical amplifier, very schematic. I have drawn for you without going into the amplifier circuit, etc. Let us say this yellow box is an amplifier. It has to have an input impedance R, and its output VO is A times V in. Whatever is the voltage in, that is multiplied by A, that is the output voltage. And of course, this amplifier will have an output resistance RO. Let's consider a voltage amplifier of voltage gain A. Say its output resistance is RO and input resistance is R. And let's say the input is provided by a signal source here. Input is provided by a signal source here. And input is provided through a coupling capacitor C, and input has a resistance RS. Any source will have a source resistance RS. This coupling capacitor is a culprit for creating the low frequency cutoff. Now let's go to a little arithmetic. If we ignore RS, which is always very, very small, what is the voltage V in? V in is equal to by the total impedance, which is R plus 1 upon j omega C, multiplied by this resistance R. Cancel R from numerator and denominator, it becomes Vs divided by 1 plus 1 upon j omega R. Clear? Oh, got V in. Now, what is the V out? V out is A times V in. So, A times, so it is multiplied by A. As simple as that. Now, at the mid-frequency band that you just saw when the gain is flat, when omega RC is much, much higher than 1, then this part is ignored. So, output voltage is equal to A times Vs. That means gain multiplied by source voltage, right? But at a certain low frequency, as the frequency becomes low, omega becomes higher, so this factor becomes lower. At certain point, omega RC is equal to 1. So at that time, output VO is equal to AVS, where 1 plus 1 upon J. 1 plus 1 upon J is equal to minus J. So what is the magnitude of VO output? If we ignore the phase of the VO, magnitude of VO is AVS by root 2. And 1 upon root 2 is 3 decibel less. Right? So this condition, omega RC is equal to 1, this is the condition of lower cutoff frequency. Omega is 2 pi f, so lower cutoff frequency FL is 1 upon 2 pi RC. Fine. So this is how, in a very simple way, I shown you by a simple calculation that how this capacitor decides the lower cutoff frequency, which is minus 3 dB frequency. Now, let us suppose two such amplifiers are connected in series or cascaded. There was a coupling capacitor C, there is another coupling capacitor. Now the output of first amplifier, I call it VO1, and input to the second capacitor, I call it VIN2, and input of the second amplifier, I call it VIN2, and output of the second amplifier, I call it VO2. Then now let's see what happens. Now, in 2 is this voltage VO1. Forget this part. This voltage VO1, and this is the potential divider. So VO1 multiplied by resistance R divided by R plus 1 upon j omega C. If you cancel R on both numerator and denominator, it becomes VO1 divided by 1 plus 1 upon j omega RC. Right? Now, this VO1 itself, you have seen in our last page, is AVS by 1 plus 1 upon j omega RC, where Vs is the source voltage. If that is so, then if we replace VO1 by this figure, then it becomes AVS divided by 1 plus 1 upon j omega RC whole square, right? If this is VN2, then what is VO2? Is A times VN2. So this is multiplied by A, so it becomes A square VS divided by this term remains as it is. Now this is a whole square. We expand this. This is 1 and this becomes this 1 minus 1 upon omega square r square c square plus 2 by j omega rc. The real part we take together, right? So if I real part, this is 1 minus 1 upon omega square r square c square. These two things together makes omega square r square c square minus 1 divided by omega rc divided by omega square r square c square. And this part 2 upon j omega rc is 2 upon j omega rc here, right? So this is the output VO2. Now at frequency, this omega RC is much, much higher than 2. In that case, this part gets ignored. So output is S square Vs, this omega square R square C square goes to the numerator divided by omega square R square C square minus 1. But omega square R square C square together is much, much higher than 1. So if you ignore 1, then you are left with only S square Vs. That means at mid frequency, gain is S square. That means product of the two gains. Since both of the gains are A, so it is A square. If it was A1 and A2, this would have been A1, A2. But at a certain frequency, at a certain low frequency, where this omega RC is equal to 2, and this V becomes S square Vs divided by omega square R square C square minus 1 divided by omega C R square C square plus 1 by J, right? Plus 1 by J. Now, if I multiply omega square R square C square, both numerator and denominator, it becomes S square Vs omega square R square C square divided by this factor plus it is multiplied by omega square R square C square. It is omega square R square C square and J multiplied, it becomes minus J, right? Now again, this 1 is ignored against omega square R square C square. So what you are left with in the denominator omega square R square C square minus J omega square R square C square. And on the numerator also you have got omega square R square C square. So you really have S square Vs divided by 1 minus J. S square Vs divided by 1 minus J. And its magnitude is S square Vs divided by root 2, right? So what we find, the lower cutoff frequency of the cascaded amplifier is given by this relation. Omega RC is equal to 2. That means FL is equal to 2 upon 2 pi RC. Whereas in single stage, it was 1 upon 2 pi RC. This is the how you can explain the low frequency performance or frequency domain performance of cascaded amplifiers. In cascading amplifier, what do we get? The gain is multiplied, but the lower cutoff frequency keeps on going up, and which makes the low frequency performance of high gain amplifiers, low frequency performance is low. I mean, you don't have as good as a low frequency performance. If you want a low frequency performance, very good. It should have a single stage amplifier. Next, we shall go to another issue which you have in your syllabus. And I want to complete that in that same lesson, which is called cascode amplifier. Cascode, so far we have discussed here, is cascaded amplifier. Now, there is another type of amplifier which is called cascode amplifier. I have seen it's in your syllabus. Cascode amplifier is not a very big thing. It's just a DC level shifter. Just a DC level shifter. Cascode amplifier is used to shift the DC level of a signal, keeping the AC amplitude intact. Now, let us say this is a signal which has a mixed DC and AC content. DC content is VDC, AC content and VAC, and the source has a resistance RS. You have this kind of sources in many places. DC and AC both together you have, right? And just using this biasing circuit, you can shift the output here. I go back. What is the output here? Output DC voltage here is VDC. But it may happen that you do not want that DC part. Somehow the DC part has come in, but you do not want it. You want to shift the DC part to zero, say. Mostly we apply it to zero, shifting to zero. But keeping the AC part intact. That you can do. DC part you can bring it to zero by simply using this biasing resistance, biasing circuit. How it works? What is the output DC? V output DC is equal to VDC plus VE. It is connected in reverse direction. VDC plus VE, that multiplied by this resistance RE divided by the total resistance RS plus RE. That minus VE, this potential. This is the DC output here, right? So this is VDC RE plus VE RE minus, just do the simplification, VE RS minus VE RE. This VE RE and VE RE gets cancelled. What we're left with is VDC RE minus VE RS divided by RS plus RE. Right? Now, so by cleverly choosing RS and RE and the value of VEE, right, you can always make the VDC, V output DC here 0. How you can do it? Just make VDC RE is equal to VE RE. If you meet this relation, then this value is 0. Fine? This value is 0 then. So you could, by the biasing circuit, you could easily make the DC 0. But what happened to my AC signal? I said AC signal should remain intact. There should be no change. But here, there is a problem. What is the output AC? By the way, for AC signal, all these DC sources are short-circuited. You know that. So output AC is also VAC divided by RS plus RE multiplied by RE. So VAC got reduced. That means the component is attenuated. So by a simple biasing circuit, you could shift the DC to 0, but signal gets attenuated. Signal getting attenuated is very problematic because we spend a lot of money in amplifying the signal. We don't want the signal to be attenuated. What is the remedy? What is the way out? Remedy is only a cascode amplifier. Now, how a cascode amplifier looks like? This is same source here, and you connect 2 transistors. And in our last picture, we connected the bias directly to the output Instead of doing that, you connect it to two transistors and put a bias voltage minus V here and put a base emitter bias to this particular transistor. This T2 acts as a constant current source because this is fixed. VBB you have decided, VE also you have decided. So it drives a constant current IE2. Current is 99% equal to IC of the T1 transistor emitter collector current, right? So this acts as a source of constant current source. And this, so the collector emitter circuit current of the transistor T1 is controlled by transistor T2 and output is taken from here. So now see, we shall see what is the DC output here. DC output here is VDC minus this resistance RS, and there is a resistance at the junction here is HFE, and this RS, and you know this current here is base current IB, and there is a source collector current or emitter current IC or IE. There is a ratio of HFE. So the drop across IE is equal to VDC minus RS multiplied by IE2 by HIE minus VB, there is a voltage drop here also, minus the current potential drop here, which is RC IE2. Right? Now, this RS is often neglected with respect to RC and HIE, etc. If you neglect this RS thing here, then what you have VDC minus VB minus RC IE2, right? So, output DC is equal to input DC minus VBE, you cannot choose because it's a transistor parameter. But RC you can choose, and IE you have already decided by controlling by the transistor T2. So by cleverly using your design as acumen here, you can make VODC to any value. You can set it to 0. So far as shifting the output DC to 0, it serves the same purpose as biasing. Now, so far as the AC signal is concerned, this output AC signal here is input AC divided by all the resistances RS plus RC plus RE plus emitter collector difference potential drop here. So all these things together, and that multiplied by RE VCE2 is the RE plus VCE2 is the output voltage here. Once again, if you ignore RS, this RS here, VAC is equal to RE VCE2 divided by RC RE plus VCE2. This is equal to, if you take this factor RE plus VCE2 out, is 1 upon 1 plus RC plus RE plus VCE2. Now, by choosing RE much more than RC, this factor can be ignored. In that case, VOAC becomes equal to VAAC. So, output AC signal here is same as the input AC signal here, like your emitter follower, like an emitter follower, right? So that was the idea of the cascode amplifier, right? So What we have learned today is how the lower cutoff frequency of amplifier changes or gets affected when you multi-stage the amplifiers for the purpose of higher gain. You add one stage after other, but at the same time, the lower cutoff frequency also gets multiplied. And another thing what we have learned is what is cascode amplifier, right? Next day, we shall go to the next topic.